So the learning objectives for this segment are going to be describing the enthalpy changes due to changes of state. So we've been talking about intermolecular reactions, intermolecular interactions, and the strength of those interactions is what controls to a large extent whether we're in a gas phase, a liquid phase, and a solid phase. Intermolecular interactions are what to a large extent stabilize the liquid phase compared to the gas phase and the solid phase compared to the liquid phase. And so we're going to look a little more about the physics and thermodynamics of these actual interactions. As you add energy or change the pressure to a system, how does it affect what phase we're in? So a concept that we'll come back to a lot in these segments is the idea of phase diagrams. And it turns out that if you have some substance and you look at its behavior as a function of pressure and temperature, that's enough to identify what phases it will be in. And again, the common phases are the solid phase, which is the high pressure, low temperature phase, the gas phase, which is the high temperature, low pressure phase, and the liquid phase, which frequently exists in between them. So a couple things about phases. So plasma, you may have heard of plasma as a fourth phase, and that's where the electrons are stripped from the nuclei and they're going freely. So it's not chemically accessible, so we don't really worry about that phase in anything that we're doing. Unless you're dealing with chemistry of the sun, it's irrelevant. And it is an oversimplification a little bit. For example, there could be multiple solid phases for some materials, polymorphs. You can have crystals that are drugs that have different forms where they're packed differently and they're sort of stuck in those different packings, and they can have relatively different properties. So you could have multiple solid phases. We generally just are going to be talking about a single stable solid phase. The simpler the molecule is, the more it tends to have a single phase. But even water can have has multiple phases, although only one phase that's accessible at most temperatures and pressures. Liquid crystals are another type of molecule that are sort of, one typical type is sort of ellipsoidal, and obviously at low temperatures it's a crystal, but you can have intermediate temperatures where it might be free to move in this direction but not in this direction, and that's a separate phase from the fully isotropic phase where really they can turn every which way like they would in a liquid. So there's some exceptions here, important exceptions. We'll be talking about sort of the major stable phases. Generally, you do see each of these phases can be characterized as solid, liquid, or gas. Solid, where it's dense, the molecules are not really moving. Liquid, where they're still touching each other, they're still attracted to each other in close proximity, but roll past each other. And gas, where they're not really interacting, or they're interacting very little. Okay, so the phase transitions, in order to get from one phase to the next, you need to add or subtract energy. For example, so there's going to, if there's three phases, then there's going to be there's going to be 6 different transitions, terms for moving from one phase to the next. For example, for liquid, going from liquid to gas is vaporization, going from gas to liquid is condensation, going from solid to liquid is melting or fusion. Fusion sounds like things are coming together, but it means the same thing as melting. Liquid to solid is freezing. And then gas to solid, for example, if you've looked at dry ice goes directly, carbon dioxide at atmospheric pressure goes directly between gas and solid phase. Sublimation is going into the gas phase, and deposition is going from gas phase into solid. And what you need to do in order to get from one phase to the next is you need to change the energy of the system. So in the case of sublimation, you're going from a relatively low energy state where you're deep in the molecules are attracted together. You need to pull them all out. And so you need to input a large amount of energy to get those out of their attractive wells from their intermolecular interactions and into the gas phase. And so that is an endothermic process. Delta H is greater than 0. Deposition, on the other hand, the gas is up here and jiggling around, not interacting, and it falls down into a state where the molecules have a lot of interaction with each other. So that is an exothermic process. As you can guess, the enthalpies are exactly opposite each other, right? If you're just reversing the process, then the enthalpy of sublimation is the opposite of the enthalpy of deposition. So you might only see one of those two tabulated because you just flip the sign and you've got the other. Same thing, vaporization, going from liquid to gas, they're mostly attracted to each other. You have to add a lot of energy in to get it to go from liquid to vapor phase, and so it's an endothermic reaction. Condensing, it's falling down the hill from a high potential energy state to a low potential energy state. So it is an exothermic reaction. Heat is given off to the environment. Same thing for liquids. When you're melting, you're going from a lower energy state to a higher energy state. And so therefore it's endothermic. The system takes in energy. It needs to pull energy from the environment. And freezing, it sounds counterintuitive for a second. The water is freezing and that's an exothermic reaction. Yes, because it's dropping down in its potential energy. So it has to give off energy to the system for that to happen. If you think about melting ice, we use melting ice to cool things. Why? Because it's an endothermic process. And so in order to go from solid to liquid, it has to pull that heat from somewhere else. And so that's the way to think about the heat required to go through these phase transitions, the heat required to break apart the intermolecular interactions, or the heat gained when the intermolecular interactions form again.